I don't think any stats class would be quite complete without at least a passing mention of this phenomenon. And this is important for a couple of reasons. First, conceptually, it's important to understand when this is occurring so that you can make more accurate causal inferences in your daily life. And the second reason is that it just gives us a good idea of how regression works as a whole. In fact, the regression technique itself was named after this phenomenon. So, at the most broad level, the reason that this phenomenon occurs is because there are random fluctuations in any variable over time that we cannot predict. And so, for reasons that are just pretty simple, and that is that there's never a direct correspondence between an IV and a DV in this life. We can never have this correlation of 1, at least in our research. And so that means that any kind of intervention that we apply that is effective, it will have some effect, but there will also be fluctuations in the DV that we cannot predict, and that's the unexplained variance or the residual. And sometimes that fools us. That residual is pretty insidious sometimes. So here's an example that I thought of. Individuals who are experiencing well-being levels that are way below their personal average are more likely to seek treatment, and that's an intervention that they're applying. However, when they get better, they immediately infer that the intervention helped, usually, when in reality, if they had not sought treatment, they probably would have bounced back to their own personal average of well-being eventually. So we don't know in this case what the effect of the intervention was versus just regression to the mean and coming back to their personal average eventually automatically anyway, or if it was a combination of both. If it was and usually it's probably that. It's probably the latter. It's probably the intervention had some effect, and then it was also just bouncing back to the mean. Now, let's say a person is experiencing a very traumatic event in their lives that may lower their average well-being over time. That's an intervention in itself. And so if that's the case, then seeking treatment may be very, very important to bring the person's personal average back up over time. So, see, we have a couple of things going on. We have random fluctuations, and then we have interventions that are actually moving people's personal averages. And we don't exactly know what's going on all of the time. So regression to the mean just means that we have these random fluctuations over time. We feel very, very good some days and not so good. And we see this also in job performance. When people are performing on the job, some days they're way above their personal average in job performance, and other days they're below, but they're always coming back to their average. And that is the idea of regression to the mean, is that we're always heading that way. It's like my personal average job performance, I'm always being pulled back to that. Okay, unless there's a really strong intervention that's giving me much better skills or something like that, which we hope for in organizations, right? That's why we apply interventions. But unless we have that, and it's a very effective, powerful intervention, I'm always going to be pulled back to my average performance over time. So over especially long periods of time, I'm going to have this average over that time period, and I'm always going to be pulled back to that. So another example is kind of along the lines of the illustration we have been using, is this GRE and GPA. So let's say in an ideal world, or actually it wouldn't be the best, but that GRE was the only predictor of GPA. So we have a correlation of 1, which would be, wow, we can predict. However, that's the only thing that affects your graduate school performance, is this test. So motivation doesn't matter. There are no random fluctuations in your performance. It's all this test. So in that case, if you scored way above your personal average on the GRE, then you would really score high on your GPA as well. You would perform very well in graduate school. However, if the correlation is not 1, if you scored super, super high above your average on GRE, then the chances are that's a random fluctuation, and you will regress back to your personal average of the GRE the next time you take the exam. And your personal average would be, in the hypothetical, that you take that GRE an infinite number of times and you take that average. So that would be your personal average, theoretically. Sounds like a very bad idea, I know. All right, so the way this plays out in real life. So I apply an intervention as a practitioner or as a scientist. Or I apply an intervention just in daily life. So let's say I'm at work and I'm a manager and I praise someone's outstanding work. They performed way above their personal average on a certain task. From what I've seen from them in the past, this particular performance is outstanding. So I feel pretty good. I'm like, yeah, they're going to do this next time because I praised them. Well, the next time they perform a similar task, it's not quite as spectacular. So I conclude that my intervention or my praise of their work, let's say I did a public recognition of some kind, it just didn't do the trick. Now, if I was thinking more like a scientist, I would understand that the odds of them repeating an outstanding performance in that sense are very small. And so I would not expect them to perform spectacularly again, but I wouldn't necessarily conclude that I should stop giving people recognition for that reason. Similarly, let's say we have a punishment situation where I'm a parent and my child behaves terribly compared to his personal average. So he behaves extremely poorly, and so I punish him in some way. And parents sometimes obviously punish very harshly. The next day or a few minutes later, the child's performing much better, more in line with his normal pattern of behavior, and I conclude as the parent that my severe and harsh punishment was a very good idea and it worked as intended. In reality, the child was probably just having a very bad day or a very bad moment, and if I would have applied a gentler technique or just left the child alone for a while, he would have come back to his average functioning. So Daniel Kahneman talks about this phenomenon in his book extensively called Thinking Fast and Slow. It's one of my favorite reads. And he basically says that this phenomenon makes us believe that we are punished for being nice and rewarded for being nasty. So I think it's important to just think about what's going on in our lives and take note of when this might be happening, and it might save us from some difficult times in our futures. Regression to the mean was also mentioned in the Lair reading earlier in the quarter, where he says that when we do research, we are often only publishing the extreme ends of a finding. So we're not finding the average effect size in the population. What we're doing is we are capitalizing on these flukes, and if we did the study 3 or 4 times, we would give this RTM phenomenon a chance to occur, and we would zero in or home in on the more accurate finding between 2 variables. So again, this is the idea of replication, how important it is to allow RTM to do its work. So we're not just publishing the extreme ends of a finding, we're publishing again and again. So the ones below the average effect size are getting thrown into the mix, the ones above and the ones that are around the average effect size, so that we're getting more of a distribution of findings to be able to make the kind of inferences that we would like to make as researchers. So that's what RTM is conceptually. So let's turn our attention to this formula before we close out this section. This formula gives us the mathematical reason for why RTM occurs. And so we have the predicted value of the DV there, but it's in z-score terms. So it's a measure of how far away it is from its average, the average of the DV. And then we have the basic correlation between x and y, and then multiply that by whatever x score we have. So the score on the predictor, but it's in z-score terms, so again it's going to be an index of how far it is away from its mean. So take a look at what happens when the RxY is 0. So again, in absence of any relationship between x and y, what happens? So if we substitute 0 in for that RxY, we see that any value of the predictor score that we stick in there, we're going to have an expected value of 0. That means the mean of the DV, remember, because a z-score is equal to 0. I'm sorry, a z-score of 0 is equal to the mean. Okay, so there we have again this idea that when we have no relationship between x and y, we are going to be saying that we expect the dv at any value of the predictor to be the mean of the dv. Now, let's go to the other extreme and substitute a 1 in for the rxy. So there's a perfect relationship. That means that we can fully predict the dv with no error, no residual, by knowing the value of the x, or the predictor value. So we stick in a predictor value that's, let's say, a very extreme score. Maybe it's -2, so it's way below its average. So it's an extremely low score. If the rxy is 1, then we will have the same for the expected value of the dv. We'll have a dv expected z-score of -2 as well. So we have no RTM happening in that case. So again, when rxy is 0, when that correlation is 0 between the two variables, we have RTM occurs fully. So there's a full regression to the mean. Any value of x, we're going to get the mean of the dv. When the correlation equals 1, we have no regression to the mean occurring. Now, as so often, as the case that we see in research, the correlation is going to be somewhere between 0 and 1 absolute values. So to the extent that it is low, we'll have RTM occurring where we have an extreme score on the predictor value is going to be muted by that rxy, whatever that is. So if it's 0.2, just substitute that into the formula and see what happens with some fake z-score for the predictor, and notice what happens on the dv. It will be closer to its average. Okay, so that r that is absolute value less than 1 will be cutting into the extreme z-score that we get for the predictor, and we are going to get a predicted value of the dv that is closer to its mean than we had with x being close to its mean. Okay, so extreme score on x will most likely yield a score in y that is closer to the mean when we have a correlation that is not perfect. So you can see in that formula how it works. Please think about this deeply, understand it conceptually, understand it mathematically, and just know how it may occur. Have some examples of how it may occur in daily life, similar to the ones that I discussed here in this segment.